Hey, what's up, my dudes? Today we're going to be talking about using the chain rule to find a function's derivative. Now, we only need to use the chain rule when we have a composite function, which basically means that we have one function nestled inside the warm embrace of another. We're talking things like natural log of x squared, or sine of 2 to the x, or the square root of tangent. None of these things have obvious derivatives, so in these cases we're going to have to use our pal the chain rule, which you can see formally written out here at the top of the screen. The chain rule says that if you want to take the derivative of something that fits the form f of g of x, then it's going to equal f prime evaluated at g of x times the derivative of g. Now, this is understandably more complicated looking than what you might see if you're looking at the product or quotient rule, which can be written in terms of u's and v's and their derivatives. Unfortunately for us, it doesn't really seem feasible to put this in terms of u's and v's. Instead, I think I have a different way around using the function notation. Why don't we go ahead and try to think of things in terms of inside and outside? Thinking in these terms, we have the wordy definition that we have underneath the formal definition there. We can think of the chain rule as the derivative of the outside function evaluated at the inside times the derivative of the inside function. Now, what this means in practice is that you need to take the derivative of the outside, and then instead of plugging in regular old x, you're going to take whatever your inside function was to begin with and plug that in. And then you're going to multiply this piece of thing times the derivative of your inside function. This will make a lot more sense after we take a look at an example or two. No matter what, it's going to be important that we stay organized. The first thing we're always going to do is classify our in prime, out, and out prime, usually in some kind of order similar to that. Once you have that information, you just plug into the formula that we have shown above. By the way, you're going to have to start to develop a sense for what's an inside function and what's an outside function. Normally, it's easiest to think of things in terms of the inside function first. Inside functions are usually contained within parentheses or radicals or even in the exponent position of a function. So let's go ahead and take a look at a couple of examples here and see if we can't start to make sense of this thing. So, our first example here asks us to find y prime when y is equal to sine of x squared plus 5x minus 2. We're going to start out by trying to figure out what's the outside function and what's the inside function. For functions with parentheses, we define the inside function as the one that's in the parentheses. So, in our case, our inside function is going to be x squared plus 5x minus 2. We may as well take the derivative of this because it's a simple power rule, right? The derivative of x squared is 2x, the derivative of 5x is 5, and then the derivative of negative 2 is 0. We don't really care to write that. Now, if we need to figure out what the outside function is, we're basically going to cross off the inside function here, and whatever is left over is going to be the outside function. Observe, if we cross off the x squared plus 5x minus 2, we're left with sine of, well, you'll see in a second here. Our outside function is going to be sine, and then we're going to get rid of the x squared plus 5x minus 2 and replace it with a simple x. The derivative of sine, or in our case, out prime, is going to be cosine of x. The chain rule says y prime is going to be out prime evaluated at the inside function, so we replace x with our in function, and then we multiply the whole thing times in prime. This means that our y prime is going to be cosine, but instead of x, we're replacing it with the inside function x squared plus 5x minus 2, and then multiplying times the derivative of the inside function. We'll put this all in parentheses to make sure that our math is in order, 2x plus 5. Normally, we take a look to see if we can simplify this. There's nothing else that we can really do, so this is our final answer. So, once again, if you have a composite function, define your in prime, out, and out prime, and then the derivative is out prime evaluated at in times in prime. Let's check out this next example here. So our in function should be obvious, but we should probably rewrite this to make it a little bit more workable when we're taking derivatives. The cube root is the same as raising something to the 1/3 power, so f of x is the same as 4x minus 11 to the 1/3. We have our inside function of 4x minus 11 inside the parentheses, much more obvious now, and the derivative of this is just going to equal the derivative of 4x, or 4. Our outside function is going to take away the 4x minus 11, and we are left with x to the 1/3. Taking the derivative here, out prime is going to be, this is a power rule again, 1/3 x to the 1/3 minus 1 is negative 2/3. We can write this to be a little bit more useful for us here. We call this 1 over 3x to the positive 2/3. Chain rule says take your out prime function, this one right here, plug in your in function for x, this guy right here, and then times by in prime. Hello, number 4. So we're going to rewrite this. Our f prime of x is going to equal 1 over 3, and then instead of x we have 4x minus 11. This was our inside function, raised to the 2/3 of course, and then all times the in prime 4. We can actually do a little bit of something with this. We can multiply that 4 and put it in the top and make things look a little bit neater for us. So our quote-unquote final derivative is 4 over 3 times 4x minus 11 to the 2/3. The lesson of this example is that if you have a radical, change it to a power, because then you can just take the derivative according to the power rule. Let's take a look at a different example where our inside function is going to be the exponent, in this case secant of x. Ready? Here we go. So our inside function, as we just said, is going to be secant of x. The derivative of secant, or in prime for our function, is going to be secant of x times the tangent of x, or just secant tan. Our outside function is going to get rid of secant x, or rather replace it with regular x. So we are going to give ourselves 5 to the x. The derivative of this function right here, out prime, is going to be 5 to the x times the natural log of 5. And at the risk of sounding like a broken record, out prime, where we plug in for our x value, and then we multiply times in prime. Time for us to put our money where our mouths are. We get h prime of x is equal to 5 raised to the inside function was secant of x times the natural log of 5. This seems like we're done, but don't forget this whole chunk right here represents out prime. We need to multiply this by the derivative of the inside, which we declared already was secant of x times tan of x. Boy, I hope you like your trig logarithms and exponentials, because there is nothing else that we can do to make this any simpler. This long string of things represents our h prime in its simplest form. As fancy as that is, we do have one more example where we're going to have to do a little bit of manipulation ahead of time. Cotan to the 4th is great, but I think we would have an easier time finding the derivative if we rewrote it as cotan of x raised to the 4th. In this way, we can clearly see that our inside function is cotan, and our outside function is not going to involve cotan, right? Our inside function, cotan of x, the derivative of cotan for us in prime is going to be negative cosecant squared of x. Our outside function is going to get rid of the cotan and replace it with x. This is just x to the 4th, and then that's very easy for us to find the derivative of. Out prime is going to be 4, x to the 4 minus 1 is 3. We have out prime, where we plug in inside for x times the derivative of the inside. This gives us an initial derivative of 4 cotan of x to the 3rd times the derivative of cotan, which we said was negative cosecant squared of x. And so we're going to give the cube to the inside of the parentheses there. The minus we're going to bring out front. And after a little bit of algebraic manipulation, we get a nice, clean final derivative of negative 4 cotan cubed of x times cosecant squared of x. And that's it, folks. Those are all the different kinds of situations that you're really going to run into anytime you're going to need to use the chain rule. Remember, stay organized. Start by defining what your inside function is, find in prime, use that to figure out what out is, take its derivative, and then the chain rule is very simply out prime, where you plug in your whole inside function for x, and then you take that and you multiply the whole thing times the derivative of the inside. I'll say that one more time for you. Out prime evaluated at in times in prime. Alright, I think I've done everything I can for you today. Now it's up to you to go out there and practice. Thank you all for coming, and I'll see you next time. Peace.